Hello everyone and welcome. I'm excited to have you here today. Today we'll be exploring the fascinating world of electricity, starting with our first topic. Current electricity. I will briefly look at what electricity is, how it flows, and why it's so important in our daily lives. So let's get started and dive into this intriguing subject. Let's take a quick overview of the key topics we'll be exploring today. We'll start with electric current, which is the flow of charge in a circuit. Next, we'll look into resistance, resistivity, conductance, and conductivity. These are fundamental when understanding how materials oppose or facilitate current flow. Then, we'll discuss drift velocity of electrons, which helps us understand how electrons move through conductors under an electric field. Moving forward, we'll explore how resistance depends on temperature and how temperature changes can affect a material's resistance. We'll also cover the EMF and potential difference of a cell, clarifying these essential concepts in electrochemistry. Following that, we'll look into the internal resistance of a cell, which influences how efficiently it can deliver power. Then, we'll examine the series and parallel combinations of cells, which are crucial in designing batteries and circuits for desired voltage and current. Afterward, we'll delve into Ohm's law, a fundamental principle that relates voltage, current, and resistance in a circuit. Finally, we'll move on to the series and parallel combinations of resistors, understanding how these configurations affect total resistance and circuit behavior. Throughout this presentation, we'll connect these concepts to build a comprehensive understanding of electric circuits and their components. Now let's take a closer look at electric current. Essentially, electric current is the flow of electric charge through a conductor. The key point here is that current can take different forms depending on how the charge moves. For example, when we talk about alternating current, or AC, its magnitude varies continuously, and its direction changes periodically. Think of the electricity that powers your home appliances. It's constantly changing direction and strength over time. On the other hand, we have what we call varying current, where the magnitude of the current changes with time, but its direction remains the same. This is typical in circuits where the current fluctuates but flows steadily in one direction. Then there's steady current, which does not vary with time at all. It flows uniformly and in a single direction, like the current in a simple battery-powered circuit. To understand these differences mathematically, if the rate of flow of charge varies with time, we express current as I equals dq divided by dt, or the differential of charge over differential of time. But if the charge flows steadily, we can simply say the current equals the total charge divided by the total time, q over t. Most importantly, remember that the electric current is defined as the amount of charge that flows through any section of a conductor in 1 second. This measurement helps us understand how much electrical energy is transmitted through circuits over time. Current is directly proportional to drift velocity. This means that as the drift velocity increases, the current also increases proportionally. Now, drift velocity is essentially the speed at which free electrons move through a conductor when an electric field is applied. Think of it as the average velocity of electrons drifting toward the positive terminal under the influence of that electric field. This concept is crucial because it links the microscopic motion of electrons to the macroscopic flow of current we measure in circuits. So, understanding drift velocity helps us grasp how electric current actually flows at a particle level, tying together the microscopic and macroscopic views of electrical conduction. Let's talk about the current density at a specific point within a conductor. Essentially, this is the amount of current flowing through a tiny, unit area of the conductor right around that point. Now, it's important to note that this area must be perpendicular to the direction of the current flow at that spot. This means we're measuring how much current passes through a small cross-sectional area, giving us a localized picture of the current flow. This concept helps us understand not just how much current is moving through a wire, but how it's distributed at a microscopic level. It's a key idea because it links the macroscopic current we measure to what's happening at the microscopic scale inside the conductor. So, in essence, current density provides a detailed view of current flow, which is crucial when analyzing electrical behavior in different materials and geometries. It connects directly to overall conduction and helps us understand how current varies within a conductor. Let's take a closer look at this fundamental concept. I alpha V or V alpha I or V equals Ri. What this means is that the electric current flowing through a conductor is directly proportional to the potential difference across its ends. In simple terms, if you increase the voltage, the current will also increase, provided that other factors like temperature or mechanical strain stay the same. This is a crucial point because it highlights how voltage and current are directly linked under consistent physical conditions. And this relationship is precisely what we describe as Ohm's law, which we'll explore further. So, understanding this proportionality helps us see how electrical circuits behave predictably, making it easier to analyze and design electrical systems. It's a cornerstone concept that ties together the entire theme of how electricity works in practical applications. Resistivity depends primarily on the nature of the material itself, not on its geometrical dimensions. This means that different materials have different inherent resistivities, which determine how much they oppose the flow of electric current. On the other hand, resistance is affected by both the material and the shape of the conductor. Specifically, resistance is directly proportional to the length of the conductor. So, the longer the wire, the higher its resistance. Conversely, resistance is inversely proportional to the cross-sectional area. Thicker wires have lower resistance. The resistance R can be expressed using the simple formula R equals V over I, where V is the voltage and I is the current. Resistance essentially opposes the flow of current, meaning it's the conductor's opposition to electric current passing through it. Understanding these relationships helps us grasp how materials and their dimensions influence electrical properties, which ties into the broader theme of how conductivity and resistivity govern electrical circuits and components. Let's talk about resistance at different temperatures. RT represents the resistance at a specific temperature T degrees C, while R0 is the resistance at 0 degrees C. Now, the temperature coefficient of resistance is a key concept here. When the temperature increases, the atoms in a material vibrate more intensely, which leads to more collisions for the electrons trying to move through the material. This increased collision rate means the electrons face more resistance, so the overall resistance of the material goes up. Essentially, as temperature rises, the internal energy of the material increases, causing these more frequent collisions and decreasing the relaxation time, the time between collisions. This is why resistance increases with temperature. Understanding this relationship is crucial because it helps us predict how materials behave in different thermal environments, which is vital for designing electronic components and circuits that are both reliable and efficient. So, the temperature dependence of resistance is a fundamental aspect of how materials respond to changing conditions, tying into the broader theme of how electrons interact within conductive materials. Now, let's take a closer look at how the color codes work for carbon resistors. The first two rings from the end are crucial because they give us the first two significant figures of the resistance value, measured in ohms. Think of these as the main digits that tell us the base number. The third ring is equally important because it indicates the decimal multiplier. This tells us whether to multiply those figures by a power of 10, effectively adjusting the resistance to its correct scale. Finally, the last ring is all about tolerance. It shows us how accurate the resistor's actual resistance is compared to the value we've read. The tolerance is expressed as a percentage, indicating the possible variation from the indicated value. Now, the table provides a quick reference to the color codes: black for 0, brown for 1, red for 2, and so on, all the way to white for 9. For tolerance, gold means 5%, silver is 10%, and no color indicates 20% tolerance. Understanding these color codes is essential because it allows us to quickly identify resistor values without needing any additional tools. This knowledge connects directly to our overall goal of understanding how resistors work and how to read their specifications accurately. Now, let's look at the parallel combination of resistors. When resistors are connected in parallel, the equivalent resistance R is found using this formula. 1R equals the sum of the reciprocals of each individual resistor. So 1R equals 1 over R1 plus 1 over R2 plus 1 over R3. An important point here is that the combined resistance R is actually smaller than the smallest resistor in the group. This makes sense because adding more paths for current reduces the overall resistance, providing an easier route for the current to flow. Switching gears to the series combination, when resistors are connected end-to-end in series, the total resistance R is simply the sum of each resistor. R equals R1 plus R2 plus R3 here. The key takeaway is that the total resistance is greater than the largest individual resistor in the set. This is because each resistor adds to the overall opposition to current flow, increasing the total resistance. These two configurations, parallel and series, are fundamental because they show us how different arrangements of resistors can dramatically change the total resistance in a circuit, which in turn affects how much current flows and how the circuit behaves overall. Understanding these concepts helps us design circuits more effectively, whether we want to minimize resistance or maximize it for specific applications. Let's take a closer look at the electromotive force, or EMF, which is essentially the maximum potential difference between the two electrodes of a cell when no current is being drawn. This means that when the circuit is open and no current flows, the EMF represents the highest possible voltage the cell can produce. Now, moving to the key points, EMF is independent of the resistance in the circuit. So, whether the circuit has high or low resistance doesn't affect the EMF itself. It's a property inherent to the cell. The term EMF is specifically used when referring to the source of this potential difference, like the battery or cell itself. It's not just any potential difference, it's the maximum potential the source can provide. On the other hand, potential difference, or PD, is the difference in potential between any 2 points within a closed circuit. Unlike EMF, PD can vary depending on the resistance and the current flowing through the circuit. It's also important to note that EMF is generally greater than the potential difference between 2 points in a circuit. However, during charging, the potential difference can actually exceed the EMF, which is a special case related to the energy being supplied back into the cell. Understanding these distinctions helps us see how EMF and potential difference relate within the broader context of electrical circuits and energy transfer. Let's talk about what influences the internal resistance of a cell. First, it depends a lot on the nature of the electrodes used. If the electrodes are made of materials with high conductivity, the internal resistance tends to decrease. That's because better conducting electrodes allow current to flow more easily inside the cell. Next, the conductivity of the electrolyte itself plays a crucial role. The more conductive the electrolyte, the lower the internal resistance. Think of it as a smoother path for the current to travel through. Another important factor is the area of the electrodes that are dipped into the electrolyte. The internal resistance is inversely proportional to this common area. So, if you have larger electrodes in contact with the electrolyte, the resistance drops because there's more surface area for current to pass through. Now consider the distance between the electrodes. When the separation increases, the electrolyte's length that the current must traverse also increases. This longer path means higher internal resistance. Essentially, the greater the separation, the more resistance the current has to overcome. Finally, all these points tie back to the overall concept that the internal resistance is the opposition offered by the electrolyte to the flow of electric current. Understanding these factors helps us optimize cell design for better efficiency. In conclusion, when the external resistance is much larger than the internal resistance, connecting the cells in series allows us to get the maximum current. Conversely, when the internal resistance is negligible compared to the external resistance, connecting the cells in parallel is the best way to maximize current. Cells are said to be connected in parallel when the positive terminals are joined together and the negative terminals are joined together. This way, the current gets divided between the cells, which can be useful for increasing current capacity. On the other hand, connecting cells in series involves joining them end to end. This means the same amount of electricity flows through each cell, effectively adding their voltages together. Understanding when to connect cells in series or parallel is crucial for optimizing the performance of a battery system, depending on whether you need higher voltage or higher current. This is a key concept in combining cells effectively to meet different power requirements.